The next series we want to look at is the alternating series. And this is a series, as the name implies, where each term alternates signs. So, for example, if we have the series negative 1/2 to the n, that's an alternating geometric series where r is 1/2, and the terms will be 1, negative 1/2, plus 1/4, and then negative 1/8, and then positive 1/16, and so on. And so this is not quite as clear cut to us because we add something and then we take a little bit away with that negative, and then we add something and we take a little bit away with the next negative, and it feels like everything we're taking away is smaller than what we were adding before, and so we still aren't really sure then whether or not the series is going to converge or diverge. So we've got a test that we can use for that. I do want to point out that sometimes an alternating series will be written in the first way, and then sometimes it'll have the alternator out in front. So it may or may not be really clear if a series is an alternating series. Sometimes it is, sometimes it isn't. So you just got to be really careful. You might list out a couple terms, something like that, just to think about it. And we'll look at some of the unusual ways that it could be written as we go through our examples. So the alternating series test, it simply says that if a sub n, our series, is positive, then the alternating series will converge if the following two conditions are met. So notice that it says it converges. So this is a test for convergence, not divergence. So be careful with that. We will never write down that a series diverges by alternating series test, only that it converges. Okay, so the two conditions that we have to have is that the limit of the series needs to go to 0, or the limit of the terms should go to 0. This is in direct, not conflict, but it's the other side of the nth term test, where when we do the nth term test for divergence, then the limit doesn't equal 0, but remember that that test doesn't tell us if it converges. This test, we have to have the limit of the sequence terms, or the series terms, equal 0, but then it won't tell us if it diverges, so just be careful about that. But anyway, so we've got the limit as a sub n, as n goes to infinity, a sub n will equal 0. And then we have the second one, and the second one says a sub n plus 1 is less than or equal to a sub n for all n greater than some k value where k is an integer. In other words, all this is saying is that a sub n is going to be decreasing, or if nothing else, non-increasing. This should make sense because in order to converge, we would need the terms to get smaller and smaller, and that's going to happen when the series is decreasing, the terms get smaller. So in the note, I just repeated what I said before, that this test only shows convergence, not divergence. If we run across a case where the limit of a sub n does not equal 0, then we're going to say that that series diverges, but we would say by the nth term test. We would never say by AST. So let's do an example. All right, example 1. Determine if the series from 1 to infinity of negative 1 to the n plus 1 over 1 to the n converges or diverges. If we look back at our test, the first thing we're going to do is take the limit of this particular sequence. Because if you look, it's not the limit of the whole series with the notation, it's just the limit of a sub n. And I'm going to back up a little bit more. If you go all the way back up here, notice that a sub n is with the alternator taken out. So the first thing you might want to do on these is determine what a sub n is. So in this particular case, oops, let me get my pencil, a sub n is just 1 over n. The alternator is the negative 1 to the n plus 1, and we just don't have to consider that in this particular part. Now, we already know that 1 over n diverges because it is the harmonic series which is diverging. You could also go ahead and run through. So the limit is n goes to infinity of 1 over n. That does equal 0, so AST would apply. And then we've got the term a sub n plus 1. That is simply going to be where we plug in the n plus 1 into the terms. So, in for every n. So where we had n here, it's now going to become n plus 1. And if you stop and think about it, this 1 over n plus 1, that denominator is always going to be larger than the denominator of 1 over n. Well, that's the bell. I'm going to stop here. Okay, so now let me pick back up where I stopped when I was so rudely interrupted. So we were doing our comparison of a sub n plus 1 and a sub n. And what we see is that a sub n plus 1 is in fact less than a sub n because the denominator of a sub n plus 1 is larger than the denominator of a sub n. So we can go ahead and say that it's less than that for all n. And therefore, because the two conditions were met, that's all you had to do is those two conditions. It's horrible, therefore. Then we're going to be able to draw our conclusion. So therefore, a sub n converges by AST. If the first one had not been met, if the limit had not been met, we would say that it diverges by the nth term test. If the second condition had not been met, then we would not have been able to apply AST, and we would have gone and looked for a different test to run. So, all right, let's look at our next example. Example 2. Determine if the sum from n equals 1 to infinity of n over negative 2 to the n minus 1 converges or diverges. You want to realize that this is an alternating series, and if you have a difficult time seeing it, then we could rewrite it so that you can see it a little bit better. But, if you can see it like this, then you're good. And so what we would do is we would rewrite it. We put the alternator out in front. So our alternator is the negative 1. I'm going to leave the 2 in the bottom. I'm just going to take out the negative 1. So it's negative 1 to the n minus 1 times everything that's left over to the n minus 1. Okay? And that's an n on top. It doesn't look like one. And so that, that makes it a little bit clearer that it's an alternating series. You don't have to rewrite it this way. That was just for since you're new to it, if you had any difficulty seeing it. Okay, so we're going to let a sub n equal, and remember it's without the alternator. So that is another advantage to rewriting the series this way, is because a sub n is just n over 2 to the n minus 1. It's not negative 2 to the n minus 1. So be careful with that. This is positive, and that's one of our conditions in the test that we needed to just make sure first. And then the limit as n goes to infinity of n over 2 to the n minus 1. So which one is going to get bigger? Is just n going to grow bigger than 2 to the n minus 1? Or vice versa? And, this is another situation where if you plug in some numbers, you ought to be able to see it. Early on, down at small numbers, the values might be kind of close. But, if we get up into, really big numbers, 10 over 2 to the 9, that bottom's going to be huge. And so it really is going to grow. The bottom's going to grow much faster than the top, and so we are going to have a limit that goes to 0. So the last step is to determine what a sub n plus 1 is, and a sub n plus 1 would simply be n plus 1 over 2 to the n plus 1 minus 1, and that's because I'm plugging n plus 1 in for every n in the a sub n term. So this is n plus 1 over 2 to the n. Now, don't go thinking that n plus 1 is going to make a huge difference in the numerator. That's the difference between a million and a million plus 1, right? Well, 2 to the million is going to be ginormously larger than a million plus 1. So that plus 1 in the top doesn't make much difference. The denominator is going to be way bigger, and it's definitely going to be a lot larger than 2 to the n minus 1. So, the numerators are very close to each other in size. The denominators, the new one in a sub n plus 1 is going to be much larger. So a to the n plus 1, or a sub n plus 1, is definitely going to be bigger than a to the n. I'm sorry. The denominator of a sub n plus 1 is definitely going to be bigger than the denominator of a sub n. Therefore, the fraction that's the term of a sub n plus 1 will be smaller than a sub n, which is what our alternating series test requires. So therefore, a sub n converges by AST, by the alternating series test. Okay? All right, so let's look at example 3. I'm going to scroll up just a little bit, or I'm going to draw a line. Okay, hold on just a second. Let's try this. There we go. All right, let me erase that silly line. All right. Oh, it's not letting me erase it. Oh, my goodness gracious. Okay, so we're going to have a line in our screen. Sorry. All right, example 3. Here we have a series. It's alternating. You can see that alternator sitting out in front. The sum, as n goes from 1 to infinity, of negative 1 to the n plus 1 times n plus 1 over n. All right, so a sub n is simply n plus 1 over n. This is positive for positive n's, and the limit as n goes to infinity of n plus 1 over n is going to be 1. So therefore, since this does not equal 0, then this does not meet the criteria for AST, for the alternating series test. So therefore, we can stop right there. Therefore, a sub n diverges not by AST, but by the nth term test. And you're done and can move on. So that was easy. It's always nice when something like that happens and makes your life a little bit easier. All right, so let's look at example 4. Now this one is a little odd looking. I don't see a negative 1 or a negative number being raised to a power. This is the series from n equals 1 to infinity of cosine of n pi over n. This is one of those alternating series that is in disguise because it doesn't look like an alternating series. But if you think about it, what we have here is we have multiples of pi that we're taking the cosine of. And these are all integers because n's going from 1 to infinity, but it's going on the integers. And so what we have is the cosine of pi, which is negative 1. And then we have the cosine of 2 pi, because n would be 2 next, and that would be positive 1. And then we would have the cosine of 3 pi, because n would be 3 next, and that would be negative 1. And the cosine of 4 pi is going to be positive 1. And it's going to keep going in that order. And so it is, in fact, alternating. And so we can rewrite the series of as n goes from 1 to infinity of the cosine of n pi over n, we can rewrite that as the series n equals 1 to infinity of, and then you can take out that negative 1, and you want to be careful with the exponent because, is it going to be negative 1 to the n? Is it going to be negative 1 to the n plus 1 or minus 1? And if you look, since when n equaled 1, it did end up being positive, we can just do, I'm sorry, it ended up being negative, we can just do this as n. And then when n is 2, it was positive, so it is going to have just negative 1 to the n in our alternator. And then this would be 1 because it just goes negative 1, positive 1, negative 1, positive 1 over n. All right, so that's how we can rewrite it. And then we've already seen this series. We did it in a previous example, and so we already kind of know what's going to happen. Pretending that we hadn't done it before, just to run through it, you would let a sub n be n, and then the limit as n approaches infinity of 1 over n is 0, so that meets the requirement. A sub n plus 1 would be 1 over n plus 1, and a sub n plus 1 is less than a sub n, and therefore the series as n approaches 1, as n goes from 1 to infinity, of cosine pi n over n converges by AST. All right, there you have it. There is one little extra thing to these alternating series tests that we'll look at in the next video, and that's convergence, conditional convergence versus absolute convergence. But work on these problems right now, and we'll do that, like I said, in the next video. Let me know if you have any questions. Y'all have a good one.